January 5th, 1943. South Pacific waters off Guadalcanal. The morning sun cast long shadows across the deck of the light cruiser USS Helena as sailors went about their duties with the quiet tension of men who knew death could arrive at any moment from the sky. The war in the Pacific had reached a brutal intensity. Just hours earlier, Helena had bombarded Japanese positions at Munda Airfield on New Georgia as part of Task Force 67.2. Now, as the task force withdrew southward, radar operators hunched over their screens, scanning for threats. They had learned through bitter experience that Japanese retaliation often came swift and deadly after such raids. At 0930 hours, 4 Japanese dive bombers appeared on the horizon, their distinctive silhouettes unmistakable. They were Aichi D-3A VAL aircraft, older designs slower than the newer D-4Y Judy, but their accuracy in the hands of experienced pilots made them deadly. The alarm sounded across the ship. Battle stations. Every gun crew scrambled to their positions. The Japanese planes dove toward the American task force, their bombs finding their mark on HMNZS Achilles before beginning their withdrawal. What happened next would change warfare forever. As the Japanese bombers climbed away, thinking they had escaped the range of American guns, Helena's 5-inch 38 caliber dual-purpose guns opened fire. Not with the desperate barrage of hundreds of rounds that naval doctrine demanded, just a few shells. The gun crews watched as the projectiles streaked toward the distant aircraft, now over 4 miles away. Then something extraordinary occurred. The shells exploded near the planes without hitting them directly. One bomber erupted in flames and tumbled into the ocean. Another followed moments later. The gun crews stared in disbelief. They had just witnessed something impossible by all previous standards of naval warfare. They had shot down enemy aircraft at extreme range without actually hitting them. The shells had exploded automatically when they came close enough to the targets. No timing calculations, no guesswork about altitude and speed, no frantic adjustment of fuse settings. The weapons simply knew when to detonate. Commander W.S. Deke Parsons, who documented the engagement, noted the extraordinary nature of what had just occurred. These were not lucky shots. These were precision kills achieved by a weapon that detected its own proximity to the target and detonated at exactly the right moment to maximize damage. What those sailors had just used was a secret so closely guarded that it ranked second only to the atomic bomb project in security classification. A weapon so revolutionary that military leaders feared its capture more than almost any other technology. A device that would prove 3 to 4 times more effective than conventional ammunition. Yet despite its incredible potential to save American lives, the highest levels of military command would refuse to authorize its widespread use for nearly 2 years. This is the story of the proximity fuse, the weapon the Navy initially kept to itself, the innovation that Pentagon officials deemed too dangerous to deploy on land, and the secret that would ultimately help win World War II. The problem of the empty sky. To understand why military leaders would restrict such a powerful weapon, we must first understand what made it so extraordinary and why its development seemed impossible. Before 1943, shooting down an aircraft with anti-aircraft artillery was an exercise in mathematical frustration and deadly futility. A problem was simple to understand, but seemingly impossible to solve. The sky is enormous. Aircraft are relatively small. They move at high speeds in 3 dimensions, and artillery shells, once fired, follow a predetermined ballistic path that cannot be altered. Traditional anti-aircraft guns relied on two types of fuses, both with severe limitations. Contact fuses detonated only when the shell physically struck the target. A direct hit on a fast-moving object, at distances often exceeding several miles, the mathematical probability of success was vanishingly small. Time fuses exploded at a specific moment after firing, set before the gun was fired. Gun crews had to calculate the exact moment when the shell would be nearest to the aircraft, accounting for the aircraft's altitude, speed, direction, rate of climb or descent, wind conditions, and the ballistic trajectory of the shell itself. Any error in these calculations, even by a fraction of a second, meant the shell would explode harmlessly in empty air while the enemy plane flew past untouched. The statistics from the early war years were grim and demoralizing. At the start of the war in Europe, it took an estimated 20,000 rounds of anti-aircraft ammunition to shoot down a single enemy aircraft. Some estimates from the Norwegian campaign and the Battle of Britain suggested figures as high as 100,000 rounds per kill. Even the most optimistic assessments from experienced gun crews suggested at least 2,500 rounds were needed for each aircraft destroyed. Naval vessels and ground installations expended enormous quantities of ammunition, with little to show for it. Ships returned to port with their magazines depleted and enemy aircraft still dominating the skies above them. The human cost of this inefficiency was measured in blood and steel. Japanese dive bombers and torpedo planes ravaged American naval forces in the Pacific. At Pearl Harbor, at the Coral Sea, at Midway, American sailors died because their anti-aircraft guns could not reliably stop attacking aircraft. German aircraft threatened convoys crossing the Atlantic, sinking merchant vessels carrying vital supplies to Britain and the Soviet Union. Allied ships faced constant aerial attack with defensive weapons that were, in practical terms, barely more effective than small arms fire. Scientists and military planners across all the warring nations knew there had to be a better solution. The concept of a proximity fuse, a shell that could detect its target and detonate automatically at the optimal distance for maximum damage, had been discussed in military journals and research laboratories for decades. The British had begun preliminary research in 1939, spurred by the growing threat of German air power. The Germans themselves had initiated at least 30 different proximity fuse programs, with some sources documenting as many as 50 separate research efforts. The Japanese experimented with acoustic and magnetic detection systems. Everyone recognized the transformative potential of such a weapon, but recognizing potential and creating a functional weapon were entirely different challenges. The technical obstacles seemed insurmountable with 1940s technology. Every major power had attempted to develop proximity fuses with varying degrees of failure. The Germans had been particularly active. Their programs included the Kranich acoustic fuse, Rheinmetall-Borsig, which attempted to detect aircraft by sound, the Fuchs program, AEG Berlin, which explored radio proximity detection similar to the American approach, the Grimm project, which investigated electromagnetic detection, and the Kugelbitz electrostatic fuse, Rheinmetall-Borsig, which would detect electrical field changes caused by approaching aircraft. Despite this extensive research, German programs were halted in 1940 by direct order from Hitler, who demanded all research focus on projects that could reach production within 6 months. This decision, driven by overconfidence after early victories, would prove catastrophic. When German research resumed in 1944 as the strategic situation deteriorated, it was too late. Rheinmetall had actually test-fired working prototypes by late 1944, but their facilities were overrun before production could begin. Not a single German proximity fuse saw operational service during the war, while the Americans produced 22 million. The Japanese experimented with acoustic and magnetic detection systems through their Naval Technical Research Institute. They understood the concept perfectly, but lacked the industrial infrastructure for miniaturized electronics. Japanese vacuum tubes were larger, less reliable, and could not withstand the stresses involved. Their best efforts produced laboratory curiosities that had no path to mass production. A proximity fuse would need to contain a miniature radar system capable of detecting aircraft and calculating distance in real time. This entire system would have to fit inside an artillery shell only 5 inches in diameter. The components would need to survive acceleration forces of 20,000 times gravity when fired from a naval gun. The shell would spin at 25,000 revolutions per minute as it flew through the air, creating massive centrifugal forces. The device would need to function flawlessly in rain, snow, tropical humidity, Arctic cold, and the chaos of combat conditions. And it would need to be cheap enough to manufacture by the millions. Most experts considered it impossible with existing technology. Vacuum tubes, the basic building blocks of all electronic circuits in that era, were delicate glass containers that shattered under far less stress than artillery shells endured. Even reinforced tubes failed when subjected to a tiny fraction of the forces involved in gun firing. Batteries powerful enough to run a radar system were far too large to fit in a shell nose. The radar antenna would need to be impossibly small, yet still functional. The safety mechanisms required to prevent premature detonation would need to work perfectly every single time without exception. One failure could kill the entire gun crew firing the weapon. And all of this technology would need to be crammed into a space smaller than a coffee can, then fired from a gun with explosive force. The British shared their early research with American scientists in September 1940 through the Tizard mission, a desperate intelligence exchange undertaken as Britain stood alone against Nazi Germany. Sir Henry Tizard arrived in Washington carrying a black metal deed box that contained many of Britain's most closely guarded military secrets. Among the documents were preliminary designs for a proximity fuse, theoretical calculations, and reports on failed experiments. But British scientists admitted they lacked both the industrial capacity and the specialized knowledge in miniaturized electronics to turn theory into mass-produced reality. The challenge fell to American researchers. The National Defense Research Committee, formed on June 27, 1940, assigned the project to Dr. Merle Tuve at the Applied Physics Laboratory of Johns Hopkins University. Tuve was a physicist who had spent years studying the ionosphere using radio waves, giving him exactly the background needed for this challenge. He assembled a team of physicists, engineers, and inventors from universities and private industry. They worked under conditions of absolute secrecy that rivaled the Manhattan Project itself. The project received security classification second only to the atomic bomb. Workers in the factories often had no idea what they were building. Components were manufactured separately with deliberately misleading names. The fuse was given the intentionally vague codename Variable Time, VT, to hide its true nature, even from most military personnel who would handle it. Section T, as Tuve's group became known, faced one technical crisis after another. Each problem solved seemed to reveal two new challenges. The team initially consisted of just 4 scientists in August 1940, but would eventually grow to nearly 1,000 researchers and support staff. They worked in converted buildings at Johns Hopkins and the Department of Terrestrial Magnetism at the Carnegie Institution. Security was so tight that different teams working on components often had no idea how their work related to other parts of the project. Standard vacuum tubes shattered instantly under the massive acceleration forces of gun firing. Early tests were disasters. In one documented test, engineers fired a standard radio tube from a gun and recovered only glass powder and twisted wire. Even tubes marketed as ruggedized and used in oil drilling equipment failed catastrophically. The acceleration was so violent that glass would flow like liquid. Internal elements would telescope into each other, and delicate wire grids would collapse instantly. The breakthrough came through partnership with private industry. Sylvania Electric Products, working with Section T engineers, developed special miniaturized tubes with reinforced glass, multiple support structures, and shock-resistant internal components. These tubes were unlike anything previously manufactured. They started with hearing aid tubes, the smallest available, and modified them extensively. Additional glass supports were added at critical stress points. Lead wires were shortened to just 3/8 of an inch to reduce flexing. Special tungsten alloy filaments replaced standard materials. The tubes were filled with special gas mixtures at precise pressures to prevent electrical arcing under stress. But even these improved tubes failed repeatedly in early tests. In one particularly frustrating series of experiments in late 1941, 900 consecutive tubes were destroyed without a single success. Engineers tried everything imaginable. They embedded the tubes in wax, which melted from heat, oil, which leaked, rubber compounds, which deteriorated, and various plastics, which cracked under stress. But even these improved tubes failed repeatedly in early tests. In one particularly frustrating series of experiments in late 1941, 900 consecutive tubes were destroyed without a single success. Engineers tried everything imaginable. They embedded the tubes in wax, which melted from heat, oil, which leaked, rubber compounds, which deteriorated, and various plastics, which cracked under stress. One engineer suggested suspending the tubes in mercury, too heavy. Another proposed using human blood plasma as a cushioning medium, tested but impractical. The solution came from an unexpected source, Dr. James Van Allen, who would later discover the Van Allen radiation belts, was then a young physicist on the team. He suggested using a wax and oil combination in precise ratios, with the tubes mounted at specific angles to distribute stress. After thousands of configurations, they found that tubes mounted at 30 degrees to the shell's axis, cushioned in a mixture of Saracen wax and transformer oil, could survive about 70% of test firings. This was deemed acceptable for wartime production. The battery problem seemed equally insurmountable. Standard batteries were far too large and could not activate instantly. The solution, when it came, was ingenious and counterintuitive. Engineers created a tiny glass ampule containing liquid electrolyte. The ampule sat inert until the shell was fired. When the gun fired, the massive acceleration shattered the glass, and centrifugal force from the shell's spin drove the liquid outward to contact carefully positioned metal plates. This initiated a chemical reaction that generated electrical current. The battery literally activated itself through the very forces that threatened to destroy it. The radar system required innovations that pushed the boundaries of electronics technology. Traditional radar systems were enormous installations weighing tons. The proximity fuse radar had to fit in a space the size of an ice cream cone. The transmitter and receiver had to share a single tiny antenna, no larger than a pencil. The circuitry needed to distinguish between the radio signal it was transmitting and the much weaker reflection bouncing back from the target. Section T engineers developed an ingenious autodyne detector circuit that could sense minute changes in signal strength as the shell approached its target. When the reflected signal exceeded a specific threshold, indicating the target was within lethal range of the shell's fragments, the firing circuit would trigger the detonation. But detecting proximity alone was not enough. The fuse had to be smart enough to avoid false triggers. A shell fired over water could not be triggered by reflections from ocean waves. A shell fired in rain could not mistake water droplets for aircraft. Engineers added sophisticated wave suppression circuits that ignored long-duration signals from stationary surfaces while remaining sensitive to the characteristic reflections from moving aircraft. They built in time delays so the fuse could not arm until the shell had traveled safely away from the firing ship. The arming sequence was complex, requiring multiple conditions to be met in precise order. Safety mechanisms had to be redundant and absolutely foolproof. The fuse remained completely inert until fired. The battery contained no active chemicals until the ampule shattered. The arming circuit required both battery activation and a minimum time of flight, typically 700 yards from the gun. The radio transmitter powered up only after the shell had spun up to the correct rotational speed using a centrifugal switch. Multiple independent systems had to align perfectly before the weapon became dangerous. One failure in any safety circuit meant a dud shell that fell harmlessly into the ocean, protecting both the gun crew and the secrets inside the fuse. The first successful test came on August 12, 1942, when the newly commissioned light cruiser USS Cleveland conducted live fire tests in the Chesapeake Bay during its shakedown cruise. Radio-controlled drone aircraft served as targets. The results exceeded all expectations. Gunners shot down 3 drones with just 4 bursts on the first day. The drone aircraft were small, fast, and maneuvering, yet the proximity-fused shells destroyed them with ease. The test was so successful that the Navy canceled the planned second day of testing and immediately ordered mass production. By January 1943, after 18 months of intensive work involving thousands of experiments, the team had produced fuses that exceeded 50% reliability in test firings. By peacetime standards, this would have been unacceptable. But with American forces suffering severe losses to enemy air attack, 50% reliability of a revolutionary weapon was deemed acceptable. Production of the Mark 32 VT fuse began in November 1942. The first operational fuses reached Pearl Harbor that same month, traveling under heavy guard in sealed containers. The Pacific Fleet received 4,500 fuses by the end of the year, distributed only to select cruisers and battleships. The Navy's security protocols surrounding the new weapon were extraordinary and unprecedented. VT-fused shells could only be fired over deep water, where the depth exceeded 100 fathoms. Any dud that failed to detonate would sink to the ocean floor, taking its secrets beyond enemy reach. Ships received strict orders never to use the fuses where they might fall on land or in shallow water. The penalty for violating these orders was severe, including potential court-martial. Commanding officers had to personally approve each use. The fuses were stored in special magazines under Marine Guard. The technology was simply too valuable to risk any possibility of capture. In early January 1943, Helena put the new fuses to their first real combat test off Guadalcanal. The results exceeded all expectations. The ship's gunners fired only 22 rounds and achieved 2 confirmed kills at ranges previously thought impossible. A gunnery report filed after the engagement stated, "The value of the Mark 32 fused projectile cannot be too highly stressed. The Bureau of Ordnance had been waiting anxiously for exactly this kind of combat confirmation. Production ramped up immediately, with contracts expanding from $60 million to over $200 million within months." Throughout 1943, VT-fused ammunition proved itself in battle after battle across the Pacific. Ships firing these shells downed enemy aircraft with unprecedented efficiency. During 1943, naval guns fired 36,370 anti-aircraft rounds. Although only 25% used proximity fuses, these shells accounted for 51% of all aircraft destroyed. The mathematics were stunning and undeniable. Time-fused shells required an average of 508 rounds to destroy one aircraft. Proximity-fused shells required only 155 rounds per kill. The new technology was more than 3 times as effective as conventional ammunition. The lethal fragment area comparison told an even more dramatic story. A 5-inch time-fused shell, if it exploded at exactly the right moment and position, could spray lethal fragments across roughly 60 square feet. This required perfect timing and positioning, rarely achieved in combat. A proximity-fused shell created a lethal kill zone of 3,000 square feet, guaranteed to detonate at the optimal distance from the target. The effective target area had become 50 times larger from the perspective of the explosive. An aircraft that would have flown safely past a time-fused explosion now flew directly into a cloud of deadly shrapnel. Night engagements revealed another crucial advantage. Time fuses required accurate range and altitude data to set the detonation time. At night, without visual confirmation, these calculations became even more difficult and unreliable. Radar could track aircraft position, but could not always provide the precision needed for time-fuse settings. Proximity fuses eliminated this problem entirely. The shell found its own target regardless of visibility conditions. Night-kill ratios increased by 370% when ships used VT ammunition. Japanese pilots, who had previously used darkness as protection, suddenly found themselves just as vulnerable as in daylight. Admiral William Halsey, commanding naval forces in the South Pacific, recognized the strategic implications immediately. Japanese torpedo planes had been making devastating nighttime attacks on American ships throughout 1942. The darkness protected the attackers and limited defensive fire to wild barrages aimed at engine noise. With proximity fuses and radar-controlled gun directors, this advantage evaporated overnight. Ships could engage aircraft effectively in pitch darkness at extended ranges. Japanese aircrew losses mounted dramatically. The tactics that had terrorized the fleet became suicide missions. By late 1943, Japanese naval aviation was suffering unsustainable losses, partly due to the proximity fuse's effectiveness. Yet even as Navy ships reaped these benefits, Army commanders in Europe fought with one hand tied behind their backs. They knew the proximity fuse existed. Intelligence reports and liaison officers had informed them of the Navy's success. They knew it could save their soldiers' lives. General Dwight Eisenhower, Supreme Allied Commander in Europe, had seen the statistics, and they had been refused permission to use it. The Pentagon's logic was based on legitimate security concerns that seemed reasonable at the time. Every artillery shell fired over land carried an inherent risk. Some shells would inevitably malfunction and fail to detonate. Some would fall in contested territory, where German forces might recover them. If the Germans captured even one intact fuse and successfully reverse-engineered it, the consequences could be catastrophic. German engineers might develop their own proximity fuses for the anti-aircraft guns defending the Reich. The American and British strategic bombing campaign depended on being able to reach targets deep in Germany. If German flak batteries suddenly became 3 to 4 times more effective, bomber losses would become unsustainable. The air war over Europe would be lost. Intelligence reports suggested German science was fully capable of understanding and replicating the technology if given a working example. German electronics firms like Telefunken and Siemens had sophisticated research facilities. German scientists had already experimented with various proximity fuse designs, though none had reached production. There was also fear of German jamming technology. If enemy scientists figured out the radio frequency used by the fuses, they might develop electronic countermeasures. False signals could trigger premature detonation or prevent the fuses from working at all. The advantage would be neutralized, and the secret revealed for nothing. Better to maintain strict operational security than risk these scenarios. So the Pentagon maintained its embargo through most of 1944. The Navy could use proximity fuses over deep water where duds would sink beyond recovery. But the Army could not use them in Europe, where every shell mattered. This decision had devastating consequences, measured in American blood. Time-fused artillery in the European theater continued to require thousands of rounds to achieve meaningful results. German formations moved with relative impunity because Allied artillery lacked the precision to stop them consistently. American soldiers died while a weapon that could save them sat in warehouses waiting for authorization that might never come. Army commanders grew increasingly frustrated as 1944 progressed. They were fighting the Wehrmacht with inferior technology while a war-winning weapon remained restricted. General Dwight Eisenhower understood exactly what the proximity fuse could mean for his troops. He had reviewed the Navy's combat data showing threefold improvements in effectiveness. He knew that American soldiers were dying unnecessarily because of what he considered overly cautious security policy. And he was not a man who accepted unnecessary casualties quietly. The military situation grew increasingly desperate by late 1944. Despite successful D-Day landings in June and the liberation of France, German forces were far from defeated. They had stabilized their lines along the German border and were preparing a massive counteroffensive. Unknown to Allied intelligence, Hitler had assembled a strike force of 250,000 soldiers, nearly 500 tanks, and 2,000 artillery pieces in the Ardennes forest. A German plan, codenamed Operation Watch on the Rhine, aimed to split the Allied armies, recapture the vital port of Antwerp, and force the Western Allies to negotiate a separate peace. On December 16, 1944, at 5:30 in the morning, Germany launched its surprise offensive. The attack began with a massive 90-minute artillery barrage that stunned American forces. 250,000 German soldiers, supported by secretly assembled tank forces, smashed into American lines along an 80-mile front. The assault hit a thinly defended sector held by inexperienced and recuperating divisions. The 106th Infantry Division had just arrived from the United States. The 28th Infantry Division was recovering from severe losses in the Hurtgen Forest. German armored spearheads, led by elite SS Panzer divisions, penetrated deep into Allied territory. The weather was terrible, with low clouds and snow preventing Allied air support. American forces reeled backward in confusion and near panic. The Battle of the Bulge had begun. American artillery fought desperately to slow the German advance, but time-fused shells proved woefully inadequate against infantry advancing across snow-covered open ground. Artillery observers struggled to provide accurate range data in the confusion. Too many shells buried themselves in the soft earth and snow, detonating harmlessly underground. Too many German soldiers survived artillery barrages that should have destroyed entire units. German infantry advanced with confidence, knowing that American artillery, while dangerous, was not the precision killer it could have been. 3 days into the German offensive, with American forces in crisis, Eisenhower had seen enough. He sent an urgent message to the Pentagon through General George Marshall, Army Chief of Staff. Eisenhower demanded immediate authorization to use proximity fuses in ground artillery. He argued that the strategic situation overrode security concerns. If the Germans broke through to Antwerp and split the Allied armies, the entire campaign would collapse. The war would be prolonged by months or years. The risk of captured fuses, terrible as it might be, was less than the risk of losing the campaign. The Pentagon relented with remarkable speed. On December 21, 1944, all restrictions on proximity fuse use were removed. Within hours, 200,000 shells with VT fuses, code-named POSIT to maintain some operational security, were released from depots and rushed to the front lines. Artillery battalions received hurried briefings on the new ammunition. Most gun crews loaded the shells with no clear understanding of how they worked. Only promises that they were far more effective than anything previously fired. The results were immediate and devastating. American artillery that had been marginally effective against German infantry suddenly became a precision-killing machine. Shells exploded perfectly at treetop height without requiring any time fuse calculations. Every round detonated at the optimal height to spray fragments across the maximum area. German soldiers, advancing across snow-covered fields, found themselves in kill zones with no protection. Units that had felt relatively safe from time-fused artillery, because heavy clouds prevented accurate observation, now died in droves. The bad weather that was supposed to protect them made no difference to proximity fuses that needed no external targeting data. General George Patton commanded the Third Army as it drove north to relieve surrounded American forces at Bastogne. His artillery battalions received proximity-fused ammunition on December 22nd. The very next day, they put it to devastating use. Near Echternach in Luxembourg, a battalion of German infantry attempted to cross the Sauer River to reinforce their offensive. Patton's artillery caught them in the open. The new shells, with the funny fuses, as Patton called them in his diary, killed 702 enemy soldiers by actual body count. The German battalion ceased to exist as an effective fighting force. Patton wrote a letter to Major General Levin Campbell, Jr., Chief of Army Ordnance, expressing his amazement at the new weapon. "The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sour River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." This was not hyperbole from a man known for dramatic statements. This was sober professional assessment from one of America's most experienced combat commanders. German soldiers, captured after proximity-fused artillery strikes, described the attacks in terms of shock and complete helplessness. One prisoner from the 12th SS Panzer Division stated there was simply no defense against the new American shells. They exploded overhead with no warning, raining fragments straight down. Men in foxholes and trenches, previously protected from artillery that exploded on the ground, now died as steel fragments came from above. German commanders had no tactical response. They could not adapt to a weapon that eliminated the traditional defensive positions that had protected infantry since World War I. The 8th Infantry Division caught a German patrol in the Hurtgen Forest, using a time-on-target barrage with proximity-fused shells. All 96 Germans were found dead. The patrol was completely annihilated, without a single survivor. Such devastating results multiplied across the front as American artillery battalions learned to employ the new ammunition effectively. German offensive momentum ground to a halt by December 25th. The counteroffensive that was supposed to split the Allied armies and win breathing space for Germany instead became a catastrophic defeat that destroyed the last German strategic reserves. Allied anti-aircraft batteries also benefited dramatically from the lifted restrictions. German aircraft making desperate close support attacks suddenly faced the same lethal technology that had ravaged Japanese air power in the Pacific. 417 German planes fell to proximity-fused anti-aircraft fire during the Battle of the Bulge period. The Luftwaffe's last major offensive effort collapsed under losses it could not sustain. Air superiority, always tenuous for Germany by late 1944, became completely unattainable. The port of Antwerp demonstrated another critical application of proximity-fused technology. The Belgian port was absolutely essential for Allied logistics, handling more supplies than all other ports combined. Its capture intact in September 1944 had been a major strategic victory, but the Germans responded with concentrated V-1 flying bomb attacks beginning in October. These primitive cruise missiles, essentially pilotless aircraft powered by pulse jet engines, flew at nearly 400 miles per hour at altitudes between 2,000 and 3,000 feet. Their speed and low altitude made interception extremely difficult with conventional anti-aircraft weapons. When proximity fuses became available for the anti-aircraft batteries defending Antwerp, the equation changed overnight. Modified fuses designed specifically for low altitude, high-speed targets turned the defenses into a nearly impenetrable barrier. In one 24-hour period, 48 of the first 75 V-1s approaching Antwerp were destroyed by proximity-fused anti-aircraft fire. The success rate climbed to nearly 80% as gun crews gained experience with the new ammunition. The vital supply port remained operational throughout the winter of 1944, enabling Allied forces to maintain their advance into Germany. Without proximity fuses, Antwerp would likely have been rendered unusable, potentially stalling the Allied offensive for months. The British capital also benefited enormously from American proximity fuse technology. London had suffered terribly under V-1 attacks beginning in June 1944. The flying bombs caused extensive damage and civilian casualties, threatening to break civilian morale. British anti-aircraft defenses initially struggled to intercept them effectively, destroying less than 20%. American proximity fuses rushed to Britain and integrated into British anti-aircraft guns, transformed the defensive capability almost overnight. By the end of August 1944, anti-aircraft batteries equipped with proximity fuses were destroying 79% of all incoming V-1s. During 1 week in August, guns using proximity fuses destroyed 82% of V-1s targeted. London was saved from a weapon that might have forced consideration of evacuation plans. The kamikaze crisis and Okinawa. In the Pacific theater, the proximity fuse's importance grew even greater as Japanese tactics evolved into organized kamikaze attacks. By October 1944, Japan had lost most of its experienced pilots at the Battle of the Philippine Sea and other engagements. The Marianas Turkey Shoot in June had cost Japan over 600 aircraft and most of its remaining trained aviators. Conventional attacks by poorly trained replacement pilots stood little chance against American fighter cover and ship defenses, with loss rates exceeding 80%. Vice Admiral Takejiro Onishi, commander of the 1st Air Fleet in the Philippines, formally organized the special attack units known as kamikaze on October 19, 1944. The first unit, the Shimpu Special Attack Corps, consisted of 24 volunteer pilots flying bomb-laden Zero fighters. Onishi told the pilots they were already gods without earthly desires. Their mission was not to return. These units used aircraft as guided missiles, piloted by men who accepted death as the starting point of their mission. The first organized kamikaze attack occurred on October 25th during the Battle of Leyte Gulf. Lieutenant Yukio Seki led 5 aircraft against American escort carriers off Samar. One kamikaze crashed into the escort carrier USS St. Lo, detonating in the hangar deck among fueled aircraft. The ship exploded and sank within 30 minutes, with the loss of 143 crew members. Other kamikazes damaged the carriers Santee, Swanee, Kitkun Bay, and Kalinin Bay. The psychological impact on American sailors was profound and immediate. This was not warfare as they understood it. Naval commanders immediately recognized that proximity fuses would be critical against this new threat. Emergency orders went out to equip every ship possible with VT ammunition. Production priorities shifted. Ships heading to the Pacific received priority allocation of proximity-fused shells. Gun crews received special training on engaging kamikaze aircraft, emphasizing sustained fire at maximum range, using proximity fuses to create a wall of exploding shells. The kamikaze threat was both terrifying and initially effective. Pilots who accepted death at the outset could not be deterred by defensive fire. They would fly through flak and fighters, absorbing damage that would force conventional attackers to turn away. They required only enough control to reach their target in the final seconds. But proximity fuses proved uniquely effective against kamikazes for reasons that became clear through combat analysis. The suicidal nature of the attacks meant Japanese pilots flew predictable, straight-line trajectories directly toward their targets. No evasive maneuvers, no complex approach patterns, no pulling away at the last second. This predictability played directly to the proximity fuse's strengths. 5-inch guns firing VT ammunition required only 310 rounds per kill against kamikaze attackers, compared to 624 rounds per kill against conventional attacks. The simpler trajectory gave the Fuzes more opportunities to detect and destroy the incoming aircraft. The Battle of Okinawa from April to June 1945 became the ultimate test of anti-aircraft defenses against mass kamikaze attacks. Japan threw everything remaining at the Allied fleet supporting the invasion. Nearly 2,000 kamikaze sorties attacked American ships over 3 months of desperate fighting. The Japanese called these mass attacks kikusui, floating chrysanthemum, and launched 10 major waves. On April 6 alone, 355 kamikaze aircraft attacked the fleet. The scale was unprecedented and initially overwhelming. American naval forces suffered the highest casualties of any Pacific campaign. 26 ships sunk, 164 damaged, nearly 5,000 sailors dead, and another 5,000 wounded. But without proximity fuses, the losses would have been catastrophic, rather than merely severe. Nearly 2/3 of all VT fuses expended during the entire war were used in just the first 7 months of 1945, most of them in the waters around Okinawa. Those fuses shot down over 2,000 Japanese aircraft that otherwise might have crashed into American ships. The invasion succeeded, but at a cost that influenced American planning for the invasion of Japan itself. Post-war analysis by the Operations Research Group concluded definitively that proximity-fused shells were 3 to 4 times as effective as time-fused ammunition in anti-aircraft roles. Some specific scenarios showed even greater advantages. 5-inch naval guns firing conventional time-fused ammunition required approximately 2,000 rounds to destroy one aircraft in typical combat conditions. The same guns using proximity fuses required between 300 and 600 rounds, depending on the tactical situation. Against kamikaze attacks specifically, the advantage was even more pronounced, with some engagements showing 5 to 10 times greater effectiveness. The proximity fuse also validated a revolutionary model of military research and development that would shape American defense policy throughout the Cold War and beyond. The project demonstrated conclusively that civilian scientists, given adequate resources and clear objectives, could solve seemingly impossible technical challenges. The collaboration between academic researchers at Johns Hopkins, industrial manufacturers like Crosley and Sylvania, and military planners had produced a war-winning weapon in under 3 years, from initial concept to mass production. The industrial achievement was as impressive as the technical innovation. The proximity fuse program represents one of the greatest production miracles of World War II, comparable to the B-29 bomber or Liberty ship programs. At the program's peak in early 1945, over 110 factories operated by 87 different companies participated in proximity fuse production. This vast network employed over 100,000 workers, most of whom had no idea what they were building. The production story began modestly. In August 1942, Crosley Corporation in Cincinnati received the first production contract. Powell Crosley Jr., who had made his fortune in radios and refrigerators, converted his entire factory to fuse production within weeks. Security was extraordinary. Workers passed through multiple checkpoints. They wore color-coded badges that restricted access to specific areas. Mail was censored. Phone calls were monitored. Workers were forbidden to discuss their jobs, even with family members. Many thought they were making improved radio tubes for military radios. Crosley's plant became a model for mass production efficiency. The assembly line was divided into stages, with workers trained on single operations they repeated thousands of times. One station wound tiny coils, another soldered connections with microscopic precision. Quality control inspectors checked every 10th unit. By December 1942, Crosley was producing 500 units daily. By December 1943, production reached 3,000 units daily. At the program's peak in April 1945, Crosley alone was producing 16,500 fuses every 24 hours. RCA entered production in September 1942, converting a facility in Bloomington, Indiana. Their expertise in radio manufacturing proved invaluable. RCA engineers developed improved assembly techniques that reduced production time by 30%. Eastman Kodak's contribution went beyond assembly. Their expertise in precision optics and chemistry helped solve problems with the photoelectric cells used in some fuse variants. They also developed improved plastic components that could withstand temperature extremes. General Electric operated multiple facilities. Their plant in Schenectady, New York, assembled complete fuses. Their most important contribution came from a converted factory in Cleveland that had previously manufactured Christmas tree lights. This facility produced the tiny tungsten filaments used in the vacuum tubes, working to tolerances measured in thousandths of an inch. A single imperfection, invisible to the naked eye, could cause fuse failure. Sylvania Electric Products became the backbone of tube production. Their plant in Ipswich, Massachusetts, employed 10,000 workers in 3 shifts, operating continuously except for Christmas Day. The plant consumed enough electricity to power a small city. Special air filtration systems removed dust particles that could contaminate tubes. Workers wore special clothing to prevent static electricity. The plant produced 95% of all proximity fuse tubes, manufacturing approximately 1 million tubes every 2.5 days at peak production. By war's end, Sylvania's Ipswich facility alone had produced 5,683,032 complete fuses, more than any other single location. Major corporations worked alongside dozens of smaller, specialized firms. McQuay Norris Manufacturing Company in St. Louis produced metal components. Zenith Radio Corporation in Chicago assembled electronic modules. Wurlitzer, famous for organs and jukeboxes, manufactured precision timing mechanisms. Even Lionel Corporation, known for toy trains, produced specialized components. By war's end, American industry had produced 22 million proximity fuses, at a total cost exceeding $1 billion in 1940s currency. The cost per fuse dropped dramatically through mass production efficiency. Early hand-assembled fuses cost $732 each, making them more expensive than many automobiles. By 1945, assembly line production and manufacturing improvements had reduced the unit price to $18. This 40-fold cost reduction made the weapons economically viable for widespread use. Even at $18 each, proximity fused shells were cost-effective when their dramatically improved kill rates were considered. Quality control was obsessive throughout the program. Every batch of fuses underwent rigorous testing at multiple stages. The National Bureau of Standards operated special testing facilities. Fuses were subjected to temperature extremes from -65 degrees Fahrenheit to +160 degrees Fahrenheit. They endured humidity chambers, salt spray tests, vibration tables, and centrifuges that simulated firing conditions. Random samples from each production lot were actually fired to verify functionality.
The failure rate had to remain below strict thresholds.
Any batch showing problems triggered investigation of the entire manufacturing run. This attention to quality ensured that fuses performed reliably in combat, from the Arctic to the tropics. The secrecy surrounding the proximity fuse held remarkably well throughout the war. Despite millions of fuses being fired in combat, the Axis powers never successfully reverse-engineered the technology or developed effective countermeasures. German engineers captured some dud shells in late 1944, but could not believe the fuses actually worked as advertised. The idea of functional radio equipment surviving inside an artillery shell seemed so improbable that they assumed the captured examples were elaborate dissections or failures. They spent resources investigating countermeasures against fusing techniques the Americans were not actually using. The Japanese faced similar but even more insurmountable barriers. They captured several dud proximity-fused shells during Pacific campaigns, particularly from naval bombardments that fell on land despite regulations. Japanese researchers understood the basic principle, but their electronics industry lacked the capability to replicate the extreme miniaturization required. The gap between American and Japanese industrial capabilities had grown so wide by 1943 that even with working examples, Japanese industry could not produce equivalent weapons in meaningful quantities before the war ended. Secretary of the Navy James Forrestal, reflecting on the proximity fuse's contribution to victory, stated it helped blaze the trail to Japan. General Eisenhower, writing in his memoirs, stated, "Is the Germans had perfected and used proximity fuses 6 months earlier than we did, the invasion of Europe would have proven exceedingly difficult, perhaps impossible." These were not casual observations. These were strategic assessments from the highest levels of military command. Men who understood the narrow margins that separated victory from defeat. Yet for nearly 2 years, Army commanders were denied access to this war-winning weapon because of institutional caution that, while understandable, proved excessive. The Pentagon's security concerns were legitimate. The risk of German reverse engineering was real, but the decision to maintain the embargo, while American soldiers died with inferior weapons, represented a failure of strategic judgment. It prioritized theoretical future threats over immediate present casualties. Only when the military situation became desperate enough during the Battle of the Bulge did leadership approve what should have been authorized months earlier. The proximity fuse represented more than just a weapons advancement. It marked a fundamental shift in how military technology could be developed and deployed. It proved that electronics and automation could enhance conventional weapons to extraordinary effect. It demonstrated that small technological advantages, properly exploited, could determine the outcome of entire campaigns. Most importantly, it showed that innovation required not just brilliant science, but massive industrial implementation and the institutional courage to deploy new capabilities despite risks. The sailors aboard Helena, who fired those first combat shots in January 1943, could not have known they were inaugurating a new era in warfare. They simply knew their shells were hitting targets that should have been impossible to engage. But the officers who commanded those forces, the generals who deployed them, the admirals who organized naval task forces around their capabilities, they understood that something fundamental had changed. Warfare had entered a new phase where technological sophistication mattered as much as courage and numbers. In under 3 years, American researchers and manufacturers created a weapon that changed warfare, produced it by the millions, deployed it across 2 theaters of operation, and used it to help win the largest conflict in human history. A weapon the Navy initially kept to itself became the weapon that helped save the Allied cause when it mattered most. The innovation Pentagon leaders feared to deploy became essential to victory. That progression, from impossible to essential, stands as testament to what human ingenuity can achieve when the stakes are survival itself. The proximity fuse reminds us that transformative military advantages often require overcoming not just technical obstacles, but institutional resistance and bureaucratic caution. Innovation delayed costs lives, but when finally unleashed, revolutionary technology can change the course of history itself. The legacy of the proximity fuse extends far beyond World War II. Every modern anti-aircraft missile uses proximity fusing as standard equipment. The Patriot missiles that defended against Scud attacks in the Gulf War used proximity fuses descended directly from the Mark 32. Naval close-in weapons systems like phalanx that protect ships from missile attack employ proximity fusing. Air-to-air missiles carried by fighter aircraft worldwide detonate using proximity fuses. The technology pioneered under desperate wartime conditions became fundamental to all modern air defense. The scientists who developed the proximity fuse went on to shape American science for generations. James Van Allen discovered the radiation belts that bear his name. Many Section T researchers became leaders in the space program. The Applied Physics Laboratory at Johns Hopkins, created for the Proximity Fuse project, continues as a leading defense research institution. The model of university, industry, and government collaboration established by the Proximity Fuse program became the template for American technological development throughout the Cold War. Most importantly, the proximity fuse saved countless lives. Naval historians estimate that without proximity fuses, American casualties in the Pacific would have been 30 to 50% higher. The kamikaze threat might have forced cancellation of the Okinawa invasion. The invasion of Japan itself, planned for November 1945, might have faced insurmountable losses from suicide attacks. In Europe, the Battle of the Bulge might have succeeded in splitting Allied armies without proximity-fused artillery. London might have been evacuated under sustained V-1 bombardment. The war might have continued into 1946 or even 1947, with millions more casualties on all sides. The proximity fuse stands as proof that sometimes the most important victories come not from courage alone, though courage is essential, but from the marriage of scientific innovation and industrial might. 22 million tiny radars, each no larger than an ice cream cone, helped win the largest war in human history. They did so by solving a problem that had seemed impossible, turning the vast, empty sky into a killing field for enemy aircraft, and giving Allied forces the edge they needed when they needed it most.